For this video, this lesson, we're going to talk about properties of real numbers. There is a PDF notes, if you want to print them out and follow along, go ahead and do so. First thing we're talking about is what are equivalent expressions. Well, they're expressions that have the same value for all values of the variables, and we'll see that here in a little bit. The first property, though, is the commutative property. And the commutative property suggests that we can move things around. This is true for addition and multiplication. Here's what it says. Changing the order of the add-ins, which is an addition, or the factors, which suggest multiplication, does not change the sum or the product. Okay, so we're going to show this algebraically first. So the first one says, if we have a plus b, then that would equal b plus a. And we can show that by actually putting some numbers in there, like 4 plus 5 should equal 5 plus 4. So if we physically move these numbers around, change their order, we can see that the left and right hand side are still equal. So that's the commutative property for addition. It is also true for multiplication. If we have a times b, that should equal b times a. The order in which we multiply should not matter, and let's use the same numbers. 4 times 5 and 5 times 4, we get 20 on this side and 20 on this side. We can see that the product hasn't changed either. The next one is the associative property. This is also true for addition and multiplication. So the commutative property and the associative property are true for both addition and multiplication, but not subtraction or division. Changing the grouping of the add-ins, which again is an addition, or the factors, does not change the sum or product. Okay, so let's say we have actually three numbers here, a plus b plus c, and we add the first two together. That's how we normally do it, left, right, in order of operations. Then we have a plus b plus c. The associative property says, well, I can come back here and add these two together and then come back and add a, and it should have the same sum. So we'll pick some numbers and put them in there. So 2 plus 4 plus 6, we're going to group the first ones, and 2 plus 4 plus 6, and group the second one. So we have 2 plus 4, which is 6, and then 6 plus 6 is 12. So this side is 12. Over here we're going to add the 4 and the 6 first, which gives us 10, and then add the 2, which gives us 12. So we have 12 equals 12, so it does work. Same thing for multiplication. That says if we have a times b times c, and we multiply left to right like we normally would, that would be the same thing as a times b times c, in which we multiply this side first and then come back and multiply by a. So let's go ahead and pick some numbers, and I'm going to use the same numbers here. So 2 times 4 times 6, group those, should equal 2 times 4 times 6, and then group those. So we'll check the numbers here. So we got 2 times 4, which is 8, 8 times 6, 48. And over here we have 4 times 6, which is 24, times 2 is 48. So we can see that 48 equals 48. The product is unchanged using the associative property. The next one is the identity property for addition and multiplication. You got to pay real close attention to these because the numbers are slightly different. This one says that the sum of any real number and 0, the sum, that's the addition, of any real number and 0 is the original number, while the product, which is a times, of any real number and 1 is the original number. What does that mean? Well, here's what it looks like. So take any number, let's say n, and add 0 to it, you should end up with n again. So pick any number you want for n, say 7, we add 0 to that, and we end up with 7. We end up with itself, its own identity, so that's why we call it an identity. Okay, so this first one is the identity property for addition. The giveaway is that's a plus sign in the middle here. There is an identity property for multiplication. So we're going to use the same number n, but we're going to use the time symbol and the number 1. So how do I get n to come back out to itself? We multiply by 1. And pick a number. Let's say we do, let's do negative 10. And then times it by 1, and we end up with negative 10. So we end up with its own identity again. So you've got the identity rules for addition and multiplication. The last two properties we're going to talk about are strictly multiplication properties. The zero property of multiplication, which a lot of you are going to say, yeah, duh. The product of n and 0 is 0. Okay, so n times 0 is going to equal 0. So pick a number for n. Let's call it 9. 9 times 0 equals 0. And that seems like a dull moment, but it's actually this property here that we're going to use later on that allows us to solve for quadratics, those variables that are raised to the power of 2. We also have the multiplication property of -1. We have this one in case you have a negative variable left over where you know what to do with it. This says the product of -1 and n is simply opposite of n, or negative n. So we have n times -1, and that should give me negative n. So if we put a number in there, like 7, 7 times -1 is simply going to give me the opposite of 7. And that would work if this was a negative number also. Let's say that was a -6 times -1. That would give us a opposite of -6, which is positive 6. Here we want to identify the property. So if you want to, go ahead and pause the video and see if you can match A, B, and C up with one of these three properties. Okay, the first one has a times in it, and it's got a 0. This has a 0 too, but it's got a plus. So this is probably related to addition. This one's probably related to multiplication. So anytime we times by 0, we end up getting 0. That would be an example of the 0 property of multiplication. So A belongs with this one. This is probably the next easiest one here. This has got an addition of 0. So you started out with a number and you ended with the same number again. So you ended it with its own identity, but you used addition. So that would be an identity property of addition. And of course, by default, the associative property is the only one that's left, but we can look at this anyway. You'll notice the only difference on this side from this side is the numbers don't change order. They're still in the same order they came. The only thing that's different is the grouping symbols. We change the way we group them. Normally we add left to right, but since we have the associative property of addition, we can actually override that order of operations, so to speak, and come back here and add those numbers first, and then come forward and add. That is what these properties allow us to do. Here's an example of one. Movie ticket costs $7.75, drink is $2.40, and popcorn is $1.25. What is the total cost for a ticket, drink, and popcorn? They want us to use mental math, so this is the order in which it gave it to us. We normally add left to right. However, I recognize that a 3/4 and a quarter here makes a nice dollar, so I can do that in my head really easy. So what I'm going to do then is take this number and rotate them around like this. Okay, and I physically move them. That's called the commutative property. So I use the commutative property to redo that. Then I'm going to use the associative property to regroup the order in which I actually add. Move this over a little bit. There we go. So I'm actually going to come back here and add this together first, and then come back and add it to the 940. So I know that I've got 75 cents and a quarter, so that's $1, plus the dollar that's here makes $2, plus 7 more dollars makes $9. So I've got this added up in my head real quick because I was able to group them. And then add my 9 to 240, and then we quickly and easily see that that comes out to $11.40, and we don't need a calculator to do that. So you're looking for some patterns here that will make your mental math a lot quicker. And because it's an addition, you can actually use those commutative and associative properties to do it in your head fast. Write an equivalent expression. If you know how to do this, or you think you know how to do this, go ahead and pause the video and see what you get before I show this. Okay, this is 5 times 3n. First thing I'm going to do is take my grouping symbol and regroup the 5 and the 3, and that would be called the associative property of multiplication. So I'm going to multiply the 5 and the 3 first instead of the 3 and the n, and then come back and multiply by 5. So 3 times 5 then would give us 15 times n. And this expression is still equivalent to the original problem. It's also equivalent to the one above it. Here's another one. Go ahead and pause the video if you'd like to give this one a try before we show you the solution. Okay, on this one, I don't have like terms inside here because this has a b and this doesn't. However, I have constant values which are like terms, so I'm going to first use the commutative property of addition to rewrite what's inside the parentheses, rotate their order around. Then I'm going to use the associative property of addition to come back here and add the 4 and the 7 first. I'm sorry, the 4 and the 8. And that would give me 12. And I can't, again, add these two numbers together because this has a variable b and this doesn't, so these are not like terms. But this is an equivalent expression to the original, but it also happens to be an equivalent expression to each of the expressions above. Okay, so this is what we want in terms of a full simplified expression that's still equivalent to the original problem. The last one here has a okay, this one here might take a few extra seconds to understand. What I'm going to do is rewrite this as 6 over 1 times x over 1 times y over y using my fraction rules. And notice that y over y is actually equal to 1. So what I have here is 6 times x, which is 6x, and then I'm timesing it by 1, which is the multiplication identity property. 6 times 1 then would give us, 6x times 1 would give us 6x, and this here would be an equivalent expression to that, but it's also equivalent to the one before it and the one before it.